Okay, on to the next set of questions. This is questions 5 and 6, which deal with filters and sine waves. So for the first one here, we've got a signal v in t equals 7 sine 2 pi 150t, etc. Just a bunch of signal components as the input to an ideal band reject filter with cutoff frequencies of FL equals 165 hertz and FH equals 185 hertz. Because we've got to have a higher frequency too. Determine the time domain equation for the output signal V out. Assume the filter doesn't introduce any phase shift. Okay, so really what we're looking for here is understanding that the frequency is this component of the sine wave component, the sinusoid. So keep in mind the first number here, 7, 3, 4, and 3 is the amplitude. The component next to the 2 pi t is the frequency. We have a band reject filter with FL. The low frequency is 165 hertz and the high frequency is 185 hertz. This is similar to the band pass filter that we looked at in class. Just now it's rejecting things instead of allowing them to pass through. So we're going to reject anything between 165 hertz and 185 hertz, and that's going to be the 180 hertz gets rejected, and the 175 hertz gets rejected. The 150 and the 300 get to stay, and their amplitudes are not going to change. We know that, in reality, a real filter will probably allow these two signals through just with a lower amplitude, but for now we're just rejecting them, and we're saying it's an ideal filter, so it's getting rid of them completely. And so V out here is just going to be the combination of the two signals that we're not rejecting, which is the 7 sine 2 pi 150 hertz t plus 3 sine 2 pi 300 hertz t. That's it for that one. So moving on to question 6, the system below consists of a real, now real instead of ideal, RC low pass filter. So that's resistor and capacitor low pass filter, followed by a real, again, RC high pass filter, so resistor to capacitor high pass filter. Both of which R is 100 ohm, or 1000 ohms, and C is 159 NF. So we're going to first calculate the cutoff frequencies for the RC low pass filter and the RC high pass filter. And so here we're just using an equation from the notes that hopefully you've got on your cheat sheet, but if not, I would go ahead and write that down now. FC, so the cutoff frequency is 1 over 2 pi RC. So not too tough of an equation to remember, but just in case, write it down on that cheat sheet so you've got it ready to go. So we're plugging in here 2 pi times 1000 times 159, and we're in nano here, so 159 times 10 to the negative 9th. And that's going to come out to, if we push that calculation through our calculator, it should come out to 1000 hertz is the frequency that we're looking at here, or 1 kilohertz. And keep in mind that that's based on the fact that the frequency for the cutoff is going to be where the impedance of the resistor and the capacitor are the same. And so we look at that, and that's what we've done to get this equation. That's important for the second part, which is what is the cutoff frequency for an RC high pass filter? Well, it's the same deal, which is the cutoff is where the impedance and the capacitance are the same. So we're going to use the same equation, FC equals 1 over 2 pi RC, with the same values for our resistor and capacitor, and so our high cutoff is actually going to be the same, which is going to be 1000 hertz and or 1 kilohertz. We're just configuring these in the opposite order, right? So in the low pass filter we have the resistor followed by the capacitor. In the high pass filter we have the capacitor followed by the resistor. And that gives us different properties due to the fact that we're really exploiting that the capacitor can't discharge its energy instantly. And so next, part C, we've got suppose Y in T is a sinusoid with frequency 1000 hertz and power equals 1 watt. So we are at the cutoff frequency, and the power is 1 watt. So keep in mind, what a real filter looks like is that, we've sort of got the, max power, max amplitude until a point, and that's where we start falling off and eventually hit to 0. So, the ideal filter is just that we sort of hit this cutoff point, and then we are at exactly 0. But in reality, we start falling off at some point before the cutoff point, and then we eventually hit that cutoff point. And from the notes, we know that at the cutoff point, we are at half power. So given that we started with 1 watt, and we're passing this through the low pass filter and then the high pass filter to get that Y out, assuming that Y in is a 1 watt signal, we're going to go through two half power adjustments, right, through these two filters. So when we go through the low pass filter at the cutoff frequency and then the high pass filter at the cutoff frequency, we're going to end up with that 1 watt times 1/2 times 1/2 is going to give us 0.25 watts at the end. That's it for those two problems on filters.